Hello everyone, welcome to this first lecture about geophysics and geodynamics. This is an introductory lecture. So let's start with the question, what is geophysics? So one may ask directly, Google the question and it will return to you some definition, very concise here, geophysics, the physics of the earth. So Geo, of course, stands for the Earth, and physics stands for physics. As simple as it gets. Geophysics is in fact a very broad, interdisciplinary scientific field which focuses on the study of the physical property and dynamics of the Earth's interior and also of planets. It is a quantitative science, and to establish quantifications, the principles of physics, mathematics, and chemistry are applied all together to the study of the interior dynamics of Earth and planetary bodies. So, since it is a broad scientific field, geophysics, you can expect that it includes different disciplines, and here is a very short glance at the different disciplines that geophysics includes. So you have the scientific field here in the middle and some disciplines around. This includes mineral physics, seismology, geodesy, geomagnetism, geodynamics, geothermics, or geoelectrics. This is a non-exhaustive list of the different disciplines that are part of geophysics. So let's have a quick look at these different disciplines here. So one example of geophysical discipline is mineral physics. So mineral physics is the study of the physical and chemical properties of minerals inside the Earth's interior. So what mineral physicists aim at is understanding how material transforms into the Earth until depths which are unreachable to humans. So here you have a little sketch of the Earth structure and dynamics. So you see, for example, here the upper mantle, the lower mantle. Here are some plates which are going into a subduction zone. And you see that in the different levels of the Earth, these different layers, there are different materials. And these materials transform with increasing pressure and depth, and reversely with decreasing temperature and pressure. So the mineral physicist tries to quantify these transformations. In seismology, the focus is set on seismic waves generated by earthquakes or artificial sources. These are used to investigate the Earth interior. So with seismology, one can, for example, deduce the interior structure of the Earth, and one may try to refine our knowledge of earthquake mechanics in order to better forecast dramatic events, and also to link the tectonic activity with activation of faults, seismic activity in general. So that's an example here of a 3D globe. You see the internal structure of the Earth. So we have the mantle here, the outer core, the inner core. And you see, for example, if an earthquake is taking place here somewhere in California, you have the different rays that traverses through the different layers of the Earth, which can then be looked at in a seismogram. So you have it up to 30 minutes after the main shock here. Another field is geomagnetism and paleomagnetism. So this using the magnetic field to study the Earth. So it studies the magnetic field of the Earth, but also the variation over the geological timescale. And this helps to understand the processes in the core, because it's the core that induces the magnetic field of the Earth, but also the tectonic plate motion. So you have a sketch here of the geomagnetic field. So you see the different field lines here that are emitted by the dipole. Here's the south and north of the dipole in rotation. And you see a computer simulation next to it, which also aims at simulating the lines here of the field. And here you have another type of data. This is the paleomagnetic stripes at the bottom of the oceans. And this we will discuss more in the context of plate tectonics. But yes, plate tectonics can record the history of the geomagnetic field over time, and this reveals important information about Earth kinematics. Another discipline is geodesy. So geodesy is the scientific study of the shape of the Earth, the gravitational field, rotational dynamics also. So this can include measurement of positions at the Earth's surface and the variation over time. So for example, what is done with a GPS study. One construction made by geodesists is the geoid. So this is one of the surface that can be deduced that may relate to mass anomalies in the surface, in the interior of the Earth. What one can do also with geodesy is to image the internal structure of the Earth by, for example, inverting for density anomaly inside the Earth. Another discipline is geoelectrics and electromagnetism. So this discipline aims at investigating the subsurface of the Earth by studying the electrical and electromagnetic properties of the subsurface. So that's used a lot in mineral exploration, but also in hydrogeophysics, which aims at studying groundwater flows, and also in environmental studies. So you see, for example, a sketch here of current ejection. So you see the current lines which are traversing through one layer of the Earth, and you see the potential field lines which are in a circular shape around the injection points. With this method, one may try to reconstruct the electrical resistivity of the soil, and this can give us some information about the substructure of the Earth. So, for example, if you have a tunnel, or if you have a waste deposit, or if you have some mineral resources at depths. Another field, another discipline in the field of geophysics is geothermics. And the geothermics studies the internal heat flow of the Earth and the temperature to gain insights into the mental dynamics and also geothermal energy. So it has direct application. So that's a map here of the heat flow that can be measured at the surface of the Earth. So you see this unit of flux here, heat flux, and you see variation from blue to red. So blue are basically mostly inside the continental areas, while the red are indicating you the locations where the plate diverges, which are basically the mid-ocean ridges. This is where hot material comes to the surface and causes surface heat flow to be very high. Here's the geothermal plant, and a geothermal plant, you know that you can pump cold water down into a reservoir, and since there is a heat flux coming from the depths, this water will be able to heat up down, and you may pump hotter water back to the surface, thus producing energy on the way. So geothermics has direct implications. Another discipline which I like to focus on a little bit more later in the course is geodynamics. And geodynamics is a study of the forces, the processes, and the motions within the Earth. So geophysics tries to understand the structural evolution, but also mantle convection plate tectonics, and crustal deformation. So basically everything which relates to mechanics and thermomechanics of the Earth. So what are the tools used in geophysics? First, I would like to mention concepts and theories. So the concepts, they can be derived by observations of a natural system, or they can be constructed based on experiments. For example, here you have the sketch with the current injection inside the ground and the equipotential lines that are radially located around the point source here. And this concept can be constructed if you do a lot of measurements around the point source. It may help you building such a concept. But luckily, we also have theories that come from physics and mathematics, for example, conservation laws. And these theories can back up the concepts in a quantitative way. So for example, Faraday's law, Ampere's law, or Ohm's law can be used to study electromagnetism in the Earth. Another type of tool that can be used in geophysics is laboratory rock physics. So laboratory rock physics is basically all the apparatus, like deformation apparatus, that allow the scientists to simulate and study the conditions within the Earth by analyzing the rock properties under pressure and temperature. So for example, to measure the heat conductivity, or to measure the viscosity, to measure the density or the resistivity of rocks at high pressure and temperature. This can be directly done in the lab. So you have an example here of one of our colleagues here presenting one of his high pressure belt apparatus that is in the lab here in Goethe University. Or here you have another sketch. That's a sketch of a deformation apparatus. It's called a Griggs apparatus. You can put a sample into a very powerful press, and this press will deform the rock and give you back, for example, the effective strength of the rock sample. Another type of tool which is used a lot are field devices. So the field devices are measurement tools that can be carried out to the field or placed into an observatory. So for example, the gravimeter will allow to measure the gravitational acceleration. The seismometer can measure the displacement of the Earth's surface during the travel of seismic waves. The magnetometer can measure the magnetic field. So you see here directly outside in the field. And all this equipment can be, for example, placed into a permanent observatory, such as the Taunus Observatory, which is not far from our place. And the tools or this kind of device may also be used remotely. So for this, we talk about remote sensing. So satellites and drones can be equipped with sensors. Of course, they will be a bit different than the ones we carry on the field. But these sensors, they can capture also geological and geophysical data of a surface. So, for example, you see here the International Space Station that may send a laser array and record back some information about the surface of the Earth. Or here are gravitational field measurement made with a drone. You see along a river valley here. So this can be done remotely. And of course, if one wants to process or simply already visualize the data, one needs computers. So the computers are necessary, and high-performance computing is part of geophysics. It's essential for simulating geophysical phenomena, for example, wave propagation, fluid dynamics, or mantle convection. So you see that computers are essential from the first stage, because they may be used on the field to process geophysical data acquired with field devices, and they can be used for the simulation of, for example, global scale processes, mental convection. This is an example here of a supercomputer called the Earth Simulator, which used to be the biggest supercomputer on Earth and which use was restricted to the study of Earth dynamics. With this kind of computers, you can also run then simulations that then aim at predicting the behavior of a natural system over geological time. So, in summary, geophysics aim at studying the structure and dynamics of Earth and planet using principles of physics and chemistry. It is a broad scientific field that groups disciplines such as mineral physics, seismology, geomagnetism, geodesy, geoelectrics, geothermics, or geodynamics. It relies on theory, experiments, field and remote measurement, as well as computer simulation.